Okay, quickly looking at current electricity. From the SAGs, you'll see there are these few points, and then also these are the equations that you get on your information sheet. So I'm going to keep them handy that we make sure that we cover everything that's in the SAGs. So the basics, I'm going to start at the basics because I find that most of the time people are confused with electricity because they don't understand actually what the difference is between current and voltage. So that's where I'm going to start. So I'm going to move our SAGs and information sheet a little bit out of the way and just quickly talk about a simple circuit. So if I have that circuit there with a battery and a light bulb, you need to think, how does the light bulb actually get to shine? It needs energy, and the energy needs to get there. And those are the two things you need to think about. How does the energy get there, and where does it get the energy from? Now, the first thing, and the first, or not really the first equation, but the second equation there that you have there is current is equal to Q over T. Now, what does this mean? It means that the current is the rate of flow of charge, and you can all say that, but the current are actually particles that are moving in the circuit. Q is electrons. It's electrons moving in the circuit. And because we're not counting every single little electron, we're counting them in coulombs of electrons. So a coulomb of electrons will just be a bundle of electrons, and it's quite a big number, and the number is given to you on your information sheet. So I'm not going to go into details there. So that will be a coulomb of electrons, and coulombs of electrons can be transferred in the electric wire. Now, they can run okay, let's just close our switch. They can run as much as they want, up and down, but if they don't have any energy to give to the light bulb's not going to shine. So you need coulombs running in the circuit, but you also need energy. So what is current? We haven't actually answered that. So if I place an ammeter here, the ammeter is basically counting how many coulombs per second passes that point. So here are my orange coulombs, and they're all running, and I'm basically just counting them. So if I count 10 coulombs passing every second, in 1 second, then I know my current is going to be 1 ampere. And I can sit in the light bulb and count, and I can sit here and count, and I can sit here and count. And every time I'm going to get the same amount of coulombs because there's no other path for them to follow. They have to go like this. And that's also called a series circuit, which we get to just now. So in that circuit, no other path. Let me clean up a bit. Now we need to talk about the energy. So these coulombs are leaving the battery, and in chemistry, you've now dealt with electrochemistry. So you know that according to the chemicals inside, these electrons will leave with a certain amount of energy, and that is the EMF. And I know it comes up later, but you need to realize that the EMF is the maximum amount of energy that the battery can supply to the coulomb of charge, and that is the definition. But it's according to the chemistry. So that cannot change. The EMF of a cell is fixed. You cannot change that. So now this cell, the EMF, is that little equation already, because voltage is EMF. It's just the voltage of the cell. And it tells us how much energy the battery gives to each of these coulombs of charge that's leaving. So if I have this little coulomb of charge, it can now move through my circuit, but now it also has energy because the battery gives it energy. So if my battery has a voltage of 5 volts, it means that each of these coulombs in an ideal world will leave with 5 joules of energy. And that's what you'll see if you look at that equation. Voltage is work over charge or energy over charge. And if you look at the units, that would be then joules per coulomb. Joules is energy, so it's the energy that we load on each coulomb of charge that leaves. So each coulomb of charge here will leave with 5 joules of energy. And the 5 joules of energy it will give off along its path and come back with nothing. So if I have only the one light bulb, that light bulb will get the 5 joules of energy. So when here comes my coulomb, it gives its 5 joules of energy to the light bulb, and once it passes through, it's got nothing. It comes back because of the potential, because of the positive charge still. So If you look at the other words used, they call it potential difference. And if you think about it now, you should be able to see that. So if I connect a voltmeter here, and a voltmeter measures the potential difference or the voltage, the coulomb of charge before it enters the light bulb has 5 joules of energy. Now it gives its 5 joules of energy to the light bulb and it leaves with no energy. It has no energy left. So that means 5 joules of energy was passed over to the light bulb, but the potential difference between here and here will be 5 joules or then 5 volts. Okay, I hope you're getting that. Now, what was I thinking just now? So the current stays the same everywhere where you go, but the voltage does change. Why I said in an ideal world is, I know also this comes later, but you need to start thinking about it. Sometimes this battery isn't 100% efficient. All its chemical energy is not converted into electrical energy. And that's when we say there's some internal resistance. So some of the energy, some of the W gets used inside the battery. And that means that's what some people call lost volts. Not really lost because it's used inside the battery, but it's not available for us in the external circuit to use. So keep that in mind. This would be 5 joules given, 5 joules given off is an ideal circuit when there's no internal resistance. All right, so that's our first two equations. Current is just the rate of flow of charge. It's the amount of electrons or coulombs of electrons moving in a circuit every second. And then voltage or potential difference is the work done for every coulomb of charge. So it's the energy either gained or energy given off for every coulomb of charge that passes in a circuit. So that's your first two equations in the information sheet that we've now dealt with. Please keep your information sheet handy all the time. It's your crib note, best crib note in the world. So now we're going to move on to series and parallel circuits, which is the second thing you need to do. And now we need to look at those two things in more detail, the voltage and the current. We need to speak about those all the time. So if you look at the series circuit, let's think about current first. If we think about current, remember, it's the coulombs moving in my circuit per second. Now they only have this path to follow. And I don't think I'll be able to move it, but there we go. So this coulomb can move through the circuit and come back. If it runs without energy, it has no purpose. It could still do that because remember, conventional current from positive to negative. I'm not too fussy about that when I'm explaining. Remember, we still use conventional current from positive to negative, but these are electrons. So it is actually the other way around, but remember, conventional current, all the rules still work. So here we go, and that's the path. So if I have 10 coulombs per second passing there through ammeter 3, the current will be 10 ampere. But those same 10 coulombs per second must pass through the light bulb and ammeter 2 and that light bulb and ammeter 1. They have no other place to go. So that means that coulomb has to go everywhere, and that is why current in a series circuit stays constant. So I total, which is the total current that leaves the light bulb, is equal to I1, is equal to I2, is equal to I3. And I can carry on like that forever. So all the currents are the same. Now, when I look at the current here, I'm going to make it a different coulomb. If I look at my current there, here comes my coulomb. And now my coulomb so I'm going to actually do more than one. So I've got orange coulomb and I've got green coulomb. So remember, they're all passing per second. So say it's a different circuit, and I now have these two passing through here. So firstly, look at orange coulomb. So orange coulomb has to go through ammeter 4. So orange coulomb passes through ammeter 4, and then green coulomb passes through ammeter 4. So 2 coulombs per second passed through ammeter 4. if I look at only those two. Now, when I get here, there's a bit of a problem because now orange Coulomb can choose. It can either go there or it can go there. So let's say orange Coulomb chooses that path and green Coulomb chooses this path. So now if I look at this path, only 1 Coulomb per second passes through that path and only 1 Coulomb per second passes through this path. So here they go, and that's the path that orange Coulomb is going to take, and it's going to keep on following that path. And then I've got green Coulomb. You can't go back on a path, so green Coulomb can't go there and then come back and then go there. So that's going to be the path that green Coulomb is going to follow. So now if we look at the currents, the total current that left was the 2 coulombs. So my total current was split up between these two circuits. So my total current is then going to be equal to the current that goes through ammeter 2 plus the current that goes through ammeter 3. So that would be A4, the total there, but also A1, because as they join up again, now if we look here, once orange has passed through there and through there, now both of them will have to go through ammeter 1 again. So ammeter 1 gets the same current than ammeter 4. Now, if you have drifted, you need to wake up, because now we look at the current, the voltage. And voltage, remember, if you think back here, is energy. It's the amount of energy per coulomb of charge. It's the joules that each coulomb carries, basically. So if we now look at little green Coulomb here, if my battery has a voltage of 5 volts, okay, what does that mean? I hope you would be able to tell yourself that that means that 5 joules of energy gets loaded. Remember, voltage is equal to W over Q. 5 joules of energy gets loaded onto each coulomb of charge. So little green Coulomb leaves with 5 joules of energy. It needs to go all the way. Coulombs can't disappear. Okay, they're particles and they cannot disappear, but they can give off their energy. So when I pass through the ammeter, ammeters have very low resistance, so they will not take any of my energy away. That's also, we place them in series because they have low resistance and we want to count how many electrons pass through them. So here goes green Coulomb, and it passes through this light bulb and this light bulb and comes back. Now there's 2 identical light bulbs because it's going to work identical for now because the principles work exactly the same if they're not identical. They will just not share the energy equally. Now, if these are identical, they're going to give as much energy to this light bulb as they're going to give to this light bulb. So green Coulomb leaves with its 5 joules of energy. Remember, 5 joules per Coulomb. And it can give off half of its energy to that one and half of its energy to that one, again coming back with nothing. So if I connect a voltmeter, remember voltmeters must be in parallel. They have very high resistance and they just measures the difference in potential between these 2 points. So green Coulomb, as it leaves here, has 5 joules of energy. When it comes back, it has nothing. So across the battery as well as across the whole circuit, the voltage is 5 volts because 5 joules of energy per Coulomb was either gained by going through the battery or lost by going through the external circuit, given off to the external circuit. So now when it got here, it only gave off half of its energy here and half of its energy here. So now if I connect a voltmeter here across this light bulb here, I'm hoping that you would see that that is going to be 2.5 volts. And this one is going to be 2.5 volts. So the voltage in a series circuit will split up where the current stays constant. So now I can go and write another equation here, and I can say that V total is equal to V1 plus V2. And you will see when we do Ohm's law, we're going to come back here and it will lead us to our resistance equations as well. Now, in series, people still get it, but in parallel, you need to now super focus. So now we are looking at these coulombs. Let's say my battery still has a voltage of 5 volts. So if I connect my voltmeter across my battery, I still have 5 volts. Always tell yourself, what does that mean? It means that each of these coulombs will get 5 joules. So the battery is loading 5 joules of energy onto green coulomb and 5 joules of energy onto orange coulomb. Now, we already said that orange coulomb can only go that way. So now you have to look at that path and say, all right, if orange coulombs follows that path, how many light bulbs does it have in its path to give off electric energy to? So if you look here, it only has this one light bulb. And if it only has one light bulb and it got 5 joules of energy from the battery, I want you to think about it. If you want to pause, you can think about it and say, okay, it only has one light bulb. It has 5 joules. It's going to come back with nothing. So that means it's going to give off all 5 joules per coulomb, so 5 volts, to this light bulb. And the same with green coulomb. If green coulomb leaves, it leaves with 5 joules of energy because the battery gives 5 joules of energy to each coulomb that leaves. So now that little coulomb comes down here, passes through that light bulb and come back. It cannot go back on its path and go through this one as well. It has to go from positive to negative conventional current. And there we go. So how many light bulbs on that path there then would only be one again. So it will give off all 5 joules that it has to this little light bulb here. So again, potential difference, if I measure before and after, I would get 5 joules of energy that was given off, 5 joules per coulomb. So that is also 5 volts. So yeah, we could just say that that is now also 5 volts. And this is why in a parallel path or in a parallel connection, the total voltage is going to be equal to the voltage in the parallel branches. If there's nothing else in the circuit, obviously, is equal to V2. Please, this is, if you understand this, electricity becomes very easy suddenly. The next part is Ohm's law. So now we have to look at, Ohm's law is still there. So I'm going to quickly look at Ohm's law here. So Ohm's law says that resistance, or it's not really its law, but that brings us to the next equation, is V over I. Now, how did they get this? So what happens in Ohm's law, they connected, so please know that the order is important there. If I go to the sags quickly, if you look here at the definition, Ohm's law, now it's hiding underneath. Ohm's law says the current through a conductor is directly proportional to the potential difference across the conductor at a constant temperature. So its current is directly proportional to the potential difference. Some teachers are pedantic about the way you give it, so just give it in the right order. So now when we look at our graph, it means that current should be on our y and voltage should be on our x. So please don't rote learn that the gradient of this graph is the resistance, because it's not always going to be the resistance. In this case, it's going to be the inverse. So be careful. So if you go and do this gradient is always going to be constant because it's a direct proportion. So what Ohm did is he looked at a lot of these things, and I'm not going to go into too much detail, but he saw that depending on the resistor, this gradient will be steeper or flatter. So he basically said that voltage is directly proportional to current. Please remember that this is only if it's in one resistor, not in different resistors. So voltage in that same resistor is directly proportional to the current. And I can now add an equal sign, because remember, y equals mx plus c. There is no c. And I can now say on my y, I've got my current, and on my x, I've got a constant, and that's my voltage. But I could have done it the other way around as well. I could have said voltage is directly proportional to current, and that is what is used to get my resistance, because the higher the resistance, the more energy I'll be using, and that's my voltage will go up and it will be steeper. So the voltage is then equal to a constant times by the current, and this constant, if it's in this order with the voltage as my y, I can say then is my resistance, because more energy is used if there's a higher resistance. So this brings us to our equation that you get on your information sheet that says resistance is voltage over current, because they are directly proportional if the temperature stays constant. Remember, these are called ohmic resistors. If you do see a straight line, if you see that it curves upwards because it's using more energy, now you know it's not an ohmic resistor anymore, because the temperature has changed and it's not obeying Ohm's law anymore. All right, let's go back here quickly. Now, if we put our resistance equation in here and we say, okay, instead of V, just a bit of maths, I can use, remember, V is equal then to I times R if you look at Ohm's law. So I'm going to stick that into the equation there, and let's see what happens. So I get I times R is equal to I times R plus I times R. And this will be the totals. This will be in resistor 1, and this will be in resistor 2. Now, what you know for this is that the currents are constant. So I can divide my whole equation by the current, because they're actually the same thing. So that means I'm getting rid of all those currents, and I get that the total resistance is equal to resistor 1 plus resistor 2. And that is what you then do. If this is 5 ohms and this is 6 ohms, I haven't spoken about units much, but I'll do it now. 5 ohms and 6 ohms, you're just going to add them up. So you get 5 ohms plus 6 ohms will give you 11 ohms for a series circuit, for instance. We did say that they are equal there, so I'm going to leave it like that. So in series, we just add up the resistors to get the total resistance. Here in parallel, it's a little bit different. I'm going to take this away. Keep in the back of your mind that the voltages are constant this time. I just want to make a bit of space there. So now here, if we think about Ohm's law again, we get that I is equal to V over R. So if I take that and I substitute, because I want an equation for R, that's why I'm doing this. So now if I say that I is equal to V over R, that's for the totals, is equal to V over R for the twos, plus V over R for the threes. And now you'll see where this equation comes from, because this time the voltages will cancel out because they are constant, and I get 1 over R total is equal to 1 over R2 plus 1 over R3. And that will be the case for all resistors in parallel. Please make sure you do the maths correctly for the resistors in parallel. You can't just put equal signs. You are very prone to just putting equal signs everywhere. So let me make space for us. Yeah. So please remember the maths. If you put an equal sign, the two sides must actually be equal. So if you end up with two resistors in parallel, so for instance, you say 1 over R parallel is equal to 1 over 5, like our example earlier, plus 1 over 6, you need to do the maths properly. So you could go and do the long way and say, okay, I'm going to find a common multiple and all of that. But because we live in modern times, you could say that you can say that this is all to the minus 1, and then this is all to the minus 1, because that means we're basically swapping both sides around. So you can say that the total resistance in parallel is then equal to 1 over R1 plus 1 over R2, or however many resistors you have, but you have to say to the power of minus 1. Because what we often see is you go 1 over R parallel and you give the answer, and then you just say what there is, and you go equal, and you swap them around without actually saying what it's equal